So I want to talk about what a confidence interval is, what it gets you. Right now, we're focusing on mean. So if we're wondering about the true mean in a population of anything, age, height, weight, income, and we take a bunch of samples, each individual sample might be quite skewed. If you were doing population, for example, it would probably be skewed fairly right, because you can't have really people making negative money, but you can have people making, much money, and so it would end up skewed right. But if instead of recording individual values, you take samples of size whatever, and you take a bunch of them all the same size, and all you write down is their means. So some of them had those humongous paychecks in them, but they had these others to balance. So you just take the means, then that will be normally distributed. And the larger your sample size, the more normal it becomes. So if you have a sample size of like 10, then you might accidentally draw the sample of the 10, huge earning people. And so you'd end up with this kind of skewed right still. But if you increase your sample size to say, 30 or more, then it's really starting to get normally distributed. And I addressed this also in a previous video. So as we increase sample size, and then not only does it become more normal, but the mean of the sample means starts to get quite close to the true mean of the population. So we've taken all these samples and we've written down the means from each of them, and then we average that, and that gets very close to the population mean. So what a confidence interval does, basically now you have this normal distribution of means. So I've got this distribution, and every value represents a mean of a sample, okay? So it looks like this, which means if this is, say, 0.95 in here, then these two are the sample means that were farther than this away from the true mean. So right now this is representing the true mean. I could draw it the other way and put our sample mean here, because if we're concerned about how different it is, if I put my mean in the middle and the sample mean over here, it's the same distance. Okay, so it doesn't really matter. The point is that we're figuring out the distance from our mean to the true mean. And if we want to know then, within 95% assurance, that the true mean is between this value and this value, then what I do is I put my mean here and I create a confidence interval that goes in either direction. And if this is 0.95, then 95% of the time it's within this distance of the true mean. So the true mean is within this distance of it. Okay? So in these tails is 0.05. So in this tail is 0.025. The reason I care about this tail is just because the way our chart is. Our chart shows the left tail. And I'm trying to figure out this value here. Okay? So the 95% assurance is that 0.95 of the time it's within this range. Okay? So what I need to do is start with my mean and add some amount over here and subtract some amount to over there, and it needs to be the same amount. You could make a confidence interval that wasn't the same amount in either direction, but that would be kind of strange and more difficult. You'd have to say, find two different z-scores basically. So since this is symmetric, I only have to find one because they're the same. And if I said, you know what, I want the 0.95, but I want to randomly start over here and end up right there, you could, but you'd have to solve for two z-scores, so why do that? So pretty much nobody ever does that. So everybody always just finds this starting with the mean and going the same amount in either direction. Okay, so when we've had a list of values and we calculate the mean and the error, our error has been called standard deviation, which standard deviation says, kind of basically generally how far things get away from the average. So we still want to know how far things get away from the average, right? This is to get this done, because we know you start here and then here's 1 SD and here's 2-ish and 3 and so forth. So we want it to still be like that, but SD doesn't do it because our distribution is no longer a list of values that we gathered, it's a list of means. And so to find the standard error of those means, this is what we use instead of standard deviation. We say standard error because it's not deviating from a mean, it's a sample error, right? So when we said standard deviation, it was because everything was deviating from the mean by some amount. It wasn't an error, it's just one person's taller, one person's shorter. So it's called a deviation from the mean. So the standard deviation was sort of like an average deviation. It was the RMS error of the deviations, and RMS is an average. But now, if I take a sample and I get a mean, it's wrong. It's an error. I'm trying to guess the mean of the population, and I got a mean, and it was different from the population, so it was my error from the mean, the true mean. So we call it the standard error. So now it's just the RMS average of the errors, and we notate it this way. But it acts like an SD. Everything else basically is going to be like this. Whenever we're taking a sample and then trying to predict something, we're wrong by some amount, and that amount is an error, so it ends up being this all the time. In the case of sample means, the standard error is the standard deviation of the population divided by the square root of the number in the sample. So as your sample size gets large, this whole thing gets small. You get closer and closer accuracy as you take larger samples. So the way that your book has this to start with, they just go ahead and use this. They know it, claim to know it, and then they have used the z-table. So what we do is we say, okay, what's the z-score that gives me 0.95? So the first thing is to solve for z. And if I want 0.95, then I want over here 0.025. So I find 0.025, and it's minus 1.96. So almost -2, which was the empirical rule, but not quite. So it's negative 1.96. But remember, this is symmetric. So this one over here that has 0.975, that has 0.025 over here, is the plus version. So these are the two z-scores. Now, I've shown you before, we know z equals our value minus the mean over the standard deviation. That means z times the standard deviation equals x minus the mean. So if I add the mean, I get the value, right? So this is something that we kind of talked about before. We're going to use it heavily enough now that you should probably try to retain it a bit. But basically, I start from the middle, and I want to add 1.96 standard deviations. That's what this says. And in this direction, I want to subtract 1.96 standard deviation. So that's the negative 1.96. It comes back to this formula, but you can sort of logic-wise consider that you want to move 1.96 SDs away. So let's suppose, so now this is just made up, suppose that you had a sample and the mean was 12.1 and the standard deviation for your sample was 1.39. And let's suppose the standard deviation for the population was 1.18. Okay? Okay, sorry, I had to turn my mail off there. Okay, so suppose this was the situation and I wanted a 95% confidence interval. Then I would have on one end of my confidence interval 12.1 minus 1.96 times 1.18 over the square root of, oh, I didn't say how many were in my sample. Let's say 25. And then over here, 12.1 plus, I'm going to run out of room, 1.96 times 1.18 over square root 25. And that should be an interval. Okay, so 12.1 and 1.18. So 11.637 12.563. Okay, so there is what I get when I know the population standard deviation and I use the z-chart. But suppose that I don't know this, because why in the heck would I? If I don't know the average, and I'm taking samples to try to guess the average, so I surely don't know the average, why in the world would I know the population standard deviation? That's crazy, right? So the only standard deviation I'm going to know is my own. Okay, so here's what we do instead. We use the student's t-test, and I told this story in the seminar, but I'll tell it to you here. Long ago, Guinness had a statistician, and okay, sorry, I had a little interruption there. So Guinness had multiple statisticians, I'm sure, but they, like everyone else, used this when they only had the sample standard deviation. So they plugged this in, divided by the square root of the sample size, and called it done. And everybody did that, and they got consistently incorrect results. So the result of this should say, in the situation I just had, if I knew the population standard deviation, that 95% of intervals created this way. So now, because they were created with the population standard deviation, they would actually all have the same width, right? So however many samples we took, they would have the same width and a different center. But 95% of the time, they'd have the true mean in them. But this wasn't the case. And so a guy who worked for Guinness figured out that it was because the sample standard deviation isn't as reliable as the population standard deviation. And so he came up with a different table that allows for different sample sizes and changes based on that. And the larger your sample size gets, the more it really looks like the z-chart. And that guy, because Guinness didn't want their competition to really pay attention to the results because they wanted to have that, leg up on them, they had him publish under the name Student, and he was a student. He was a student of one of the most famous mathematicians of the time, but he just published under Student. So all his papers were written by Student, and for the longest time, the competition just ignored it. So it's called Student's t-test. So here's that chart. This one, it has this tail instead of that one. It doesn't matter for confidence intervals, of course, but because we do plus and minus, but it does not have as many values as z. So here's what it has. This side, df, stands for degrees of freedom. The degrees of freedom is one less than the sample size. So if you have a sample size of 2, you use this row. If you have a sample size 3, you use this one. Sample size of 31, you use this one. Sample size of 39, you should probably still use this one because 30 gives you a wider interval, and if you use 40, then you can't be quite whatever percent sure. This one you'll actually be a little more sure, but if you're working for a company and they say, listen, I want you to be 95% sure, and you come back and you use 40 with your sample size of 39, then you're really only like 93% sure. They won't like that. But if you're turning something that makes you, 95.5% sure, then that's fine. So use the next smaller number. And it ends at 120 because honestly, when you get past 120, it starts looking a whole lot like the Z table. But these are the only values given. So you don't have all the options that you have on a Z table. You have a bajillion different areas, and here you don't. So these are the areas instead of the Z. These are the t-scores. These are the areas. So if we want to be, for example, 95% confident, then just like before, we want that 0.025 over there. So we just look at this column, 0.025. And we said that we had 25 in our sample, so we want to come down this column to 24 because we want degrees of freedom 24, just one fewer than our sample size, and 2.064 is our t-score. So this is what I use in place of 1.96. But instead of 1.18, which I didn't really know, I used the 1.39. So now I'm going to do 12.1 minus 2.064. This is really hard to read. And the interval I'm trying to make is going to be the mean minus t times the SD divided by the square root of n. The mean plus t times the SD over the square root of n. This is the interval I'm making. Okay, so 2.064. So 2.064 here. And 1.39 there. And we get 12.674. And the minus side, 11.526. Okay, now you can see that these intervals are not very different. Mine from the t-score is a little bit bigger. That's not really unexpected. Somebody's might be smaller. If you happen to have a really tiny SD in your sample, you might get a slightly smaller. And if you have a larger SD, you'll get bigger. So in this case, if you do a bunch of different samples, they actually don't have the same width because the width is based on not just t, but the standard deviation, which will vary. So in this case, because I didn't have this population standard deviation, I could say I'm 95% sure that the true mean is within this interval. And 95% of the time it would be in somebody's interval. But somebody may have a really short interval, and that one may be, the one that doesn't get hit, or it may not be the one that doesn't get hit. So this is how you do these, not in the calculator. And then the next video tells you how to do it in the calculator, but this is the reason that you're doing this. I told you guys the other day, as far as the size of the intervals, they're altered by sample size, well, standard deviation obviously, but even if you knew the population standard deviation, they're altered by sample size and confidence level. So let's think about it like we're trying to throw darts at a dartboard, which for whatever reason is egg-shaped. And the mean is what we're throwing, and it's going to land wherever the mean is. And we want to know the likelihood that it lands in our interval. So if I asked you, how sure are you that you can hit within this tiny interval, you'd probably say, really not very, right? And if I asked you then, how confident are you that you can hit within one of these two, so within this ring, then you might say, well, fairly, a little better than that. And then what about within all of these? Then you might feel a little bit better now, but still not be, 100% sure. And then if we do this one, you're probably getting pretty confident at this point, because if this is the true size of the dartboard, this is now getting to be not all that hard to hit. And then if I add in this one, then I'm basically just asking how sure are you that you're not going to hit the wall. And I think, most people would feel fairly confident that they wouldn't hit the wall of the standard size dartboard. So your confidence grows as the places you're allowed to hit increases. So these are the places I'm allowed to hit. So as this increases, I should be more sure. And the reverse of that then is, if I'm forcing you to be more sure, this will be bigger. So as my confidence lessens, this gets smaller. So if I instead just ask for 80% confidence, this T would be a lot smaller. The width of this would be a lot smaller. But you can think about every time you ask somebody the question or write down somebody's result, that you're practicing. That's not exactly a perfect analogy, but let's say that that's how you think about it. So as your samples, so every time you ask a new person, you spend another half hour practicing darts, okay? So by the time you've asked 100 people, you've spent 50 hours practicing darts. And now you're a lot more confident, actually, that you can hit within that yellow, right? Because you've practiced a lot. So asking people gets you more control. The more people in your sample, the better control you have over your aim, basically. So if your sample size increases, this should get smaller. And it will, because if you look right here, we're dividing by the square root of it. So this gets bigger as your sample size increases, so that gets smaller, so that gets smaller, which means we're moving less from X bar in either direction, and our interval is getting shorter. So I think this completes everything that was in the seminar. That was a preparation for the video that follows this one, which has already been posted. So I'll put this one before it, and hopefully that will do it. Let me know if you have any questions.